I'm going to talk about my approach to machine and reinforcement learning. So I'm working here at this Faculty of Mathematics and Computer Science and Mechanics. I'm also associated with a company called Sports Lab. I will mention briefly at the end what's up with that. And let me acknowledge support by Nava. So you may not know me, so let me briefly present why I'm here. So I did my PhD in 2013 it was in Jagiellonian University. I did my PhD in applied math. I was dealing with differential equations, things like that, like mathematical physics, some computer simulations. And then I was briefly hired as a postdoc at University of Warsaw, and then I went to the US to do first postdoc in New Jersey, and then I did another postdoc in UC San Diego, and I got interested in machine learning about in that period, so it was after my PhD. And So I returned to University Warszawski due to the grant I obtained from Nava agency. So they support me and my small research group at the moment. So we just kicked off in September. So my research statement, okay, let me broadly present my research statement. So my goal is to bring in some new techniques, mostly from applied math into machine and reinforcement learning. And I will give you overview of what I've been doing so far and my current project, which is focused on reinforcement learning. And already I will show you some sneak preview of some preliminary results that we have for reinforcement learning. So a big part of my research is also related to so-called TDA, topological data analysis. There was one talk on Friday I noticed about that. I don't know if you've seen that talk. So I've been working on that, and especially in the context of applying TDA to machine learning. And I will show you what we can get out of that, okay? Then another big part of my research is related to verification of cyber physical systems. And this thing, you may not know this term, but it is related to reliable reinforcement learning in a way. So I will present you this part of my research also. Then I will move to my current research, which is model-based reinforcement learning for robotics, for simple robotics problems. And then finally, I just got into that is some research on performance in esports. So I will just mention what's up with that at the end. If you have some questions, you can interrupt me. Feel free to interrupt me, of course, at any point. So let's look at first part, which is TDA-based classifiers. Okay, mapper. I will explain what's going on with that. So the general idea that we had is to replace convolutional features in image classifiers by something completely different, which will be more robust. Because if you have, well, I don't have a slide about that because everyone knows that problem. If you perturb a bit image and you get, instead of a cat, you get guacamole, okay? And issues like that are coming from the fact that you have some convolutional layers and they are like stuck on top of each other. This like deep neural network, and the small error can propagate to some huge differences. So our approach was to replace these convolutional features with something else. So let's look at this mapper algorithm. It's really applied. There are many papers in Science, Nature using that algorithm. So you may have a look at that. So the idea is really simple. So there's point cloud of data. Like on this one example, there's like a hand, okay? 3D scan of a hand. There's point cloud of data. There's you prescribe some filter function. In this case, filter function is just x coordinate. Okay, so red from red to blue is scaling. So you see that these points are like red are smaller x coordinate and blue is the larger x coordinate, and we filter our point cloud like that, and then we split we take the image, we split it into intervals, and we take the pre-image. Okay, so if I take the pre-image of values here, I will get these 3 pieces of fingers. Okay, if I take pre-image here, I will get these pieces, etc. Okay, and having that structure, I can build a graph. So I'm building a graph which represents the high-dimensional point cloud in low dimension, okay? And this is super nice because people are using this to extract knowledge out of big data sets, okay? Like, for example, you have some MRI scans, and you can cluster like, you know, sick and healthy persons by looking at there's really high-dimensional brain image scans. That's one application. So what we did is to use this algorithm as a feature layer in an image classifier. So far you see I will be using this simple data sets like MNIST, fashion MNIST, because there are some issues with scalability of our approach. But the idea is you have your data set, you project it onto latent space. Latent space, you know, like PCA, you know, basic examples, like PCA, autoencoder, okay? You can use whatever you want. And then you apply the mapper algorithm to the latent space, okay? Of course, I need to do some batching because data sets are large, you know. You cannot, it's easier to deal with smaller. So we do batching and we construct we apply mapper to each batch, and we get, out of that, as I said, we get a graph. And these graphs are our features, okay? Because we can binarize them. We can binarize them and construct like a binary vector by merging all of them, and then put it into fully connected classifier, okay? Okay, so that's how it works, and let's look at the results. So I don't have much time to get into details. I will just mention briefly. So we generated some white box attacks. Okay, we couldn't do black box attacks here. You know, white box is attack. It means that you have access to the gradient, okay, basically. And this is hard here because it's hard to differentiate this binarization step. So instead we did this black box attacks, okay? Like put some random noise, Gaussian noise, salt and pepper noise, and Gaussian blur, and see how it performs. So this research just appeared it will appear in the conference, which is taking place in December in Florida. And this was a part of Alex's PhD thesis in UC San Diego, by the way. So that's him presenting this. So we find out that this approach on the simple data sets like MNIST and fashion MNIST is like small pictures of boots, of t-shirts, etc. On these simple data sets, apparently it was more robust than convolutional neural networks. So I will briefly present that this CNN convolutional is in red here, okay? It's really bad for Gaussian blur, for example, and our approach came out to be better. We used two different latent space. One was PCA, which is this dark blue, and VAE, which is this purple. Sometimes this VAE was really bad, like in this case. So we don't have yet explanation of everything what happens here, but PCA version was surprisingly more robust with respect to noise, okay? So this on this picture you see this is L2 norm of the noise, and this is normalized accuracy. So it starts with 1 and then drops because you increase the noise, right? And then, for example, you can see clearly here that convolutional neural network drops dramatically, while our mapper-based classifier kind of is still robust, especially for MNIST data set, and also you can see this phenomenon for fashion MNIST. Okay, there's a big room of improvement. Actually, I'm looking for master thesis students, maybe who could collaborate on that, and because idea is promising, and we want to extend it to more like interesting data sets like ImageNet or CFAR, or even some 3D objects data sets, because we think that this approach will be really good for 3D objects. And there's a lot of hyperparameters inside that we kind of tweaked manually, and we are looking for more scalable approaches at this point. Okay, the second part is this. Okay, that was kind of machine learning. It was a kind of machine learning thing. I said I'm going to talk about more reinforcement learning, so let me move on to the cyber physical systems research. So what is it about? So I have this collaboration with mainly 3 people, Sophie from Vienna, Arif, he's from Texas, and Radu, he's from Vienna too. And we kind of wrote 3 papers on that already. So if you are interested in more details, you can talk to me afterwards, but the idea in simple words, the problem statement in simple words is like I have environment that I know how it works, so I have a model, okay, of that environment. For example, this model here that you see is this carpal, okay, so you may know carpal. So apparently carpal has really simple model, okay, so if I assume that I know this model, I can use this approach. Model is given by differential equations. And then there's controller. In this case, this controller is trying to stabilize carpal, okay? And it's like feedback loop, okay? So this is like a really simple setting. So environment is working according to some laws, physics that I know, okay? I'm going to use this later when I'm going to talk about reinforcement learning, okay? Also, about this physics intuition. So I know physics, and then I have controller that I trained somehow, and I want to verify that it's doing, for example, what you saw, that it's stabilizing this pole, okay? And so we have algorithm for that. So as I said, if I know the model, I can apply certain mathematical techniques. One of them is interval arithmetics. And I can construct algorithms that are able to verify properties. In a sense, like if I start a carpal system, okay, in some position, it will be stabilized after some time. This type of properties. Our algorithm, okay, I'm not going to go into details, but the idea is kind of simple. It's based on so-called finite strain theory. So we construct ellipsoidal bounds on a set of states, and we propagate them in time. And this is conservative, okay? So as I said, I want to verify, so it's 100% certainty, okay? And this 100% is requires special algorithm. And this is like preliminary, okay? Because in reinforcement learning, you cannot obtain 100%, never ever, okay? So I'm saying that if you know the model, the physics exactly, you can do that, okay? But later on, I will show you how to use these intuitions in RL. So the goal here is like if you know how your car, you know the model, the physics of your car, you may want to prove that it never collides, okay? But then you may say it's easy, okay, because I have some algorithm which is just conservative, and I'm able to do that. But it's not so easy because if you get too many, too large bounds, you will get false positives. In a sense, you will see that your car will hit some unsafe region, but in practice it will not. So you need to work hard on tightness of this bounds. So we have I just want to briefly mention that we have algorithm for that, and it works well. You can see Monte Carlo simulation here for some given simple two-dimensional model. And as I said, we are obtaining 100% conservative bounds. So in this case, this is output of our algorithm. There are like there's like a ball and ellipse, and then we take intersection, and we get this bound, okay? And this is output of our algorithm that any state that you can see some Monte Carlo examples, any state will be within these bounds. So this is like marketing slide because we show here on that example that we get the tightest bound than other available tools. These are some examples from our paper. So this is how it looks in a phase space. This is comparison with other tools. So this is Carpal with linear controller. Okay, I showed you that there was like a complicated neural network on the picture, but in fact, this Carpal you can just use simple linear controller to stabilize it. So it's not a big deal. So it's not hard at all. Okay, if you know the model of Carpal, it's not hard at all to stabilize it. Actually, controller is given by this simple formula. And if you plug this in, it will stabilize always Carpal. And this is like how we verify it, okay? How it looks like in practice, verification procedure of that. And then we also apply it to a different model, which is quadcopter. It's more complicated model, but okay, it exists. So even for things like flying drone, you know the physics, okay, and it's given by this equation, so you can start playing with that. Any questions up to that point? So I will ask myself question. How to make it relevant for reinforcement learning, okay? When you don't know the exact model. So the trick is really simple. We are working on that now. We don't know where the states are and the exact model. So we can get around by using distribution, probability, okay, and distributions. So let's say I know that's my distribution of initial states, okay? So I will start with the higher probability close to some point, and then the probability is lower further away. And I know some approximate dynamics, okay, that maybe I get from my model-based RL approach or from somewhere else. And after a while, I know that this distribution will be transferred to that distribution, okay? So after some time, I will be the highest probability of finding my state will be in this point, okay? This is abstract. This state can mean like position of a car, some torque and positions of joints, or some angles, of this robotic arm. Yeah, so that's how to make it more relevant to ML-RL. So yeah, let me now go into the third part, which is towards reliable reinforcement learning. So I call it towards because we just kicked off the project and we have only, I will show you some sneak preview what I've been working with my PhD students, Jacek and Misha. So let's say you know the RL, how it works in general. Okay, there's agent and there's environment, and they interact. Agent sends an action to environment, and environment sends state and state and reward back to agent, and it's like a loop. And you try to train. And so we look at this. I don't know if you know OpenAI Gym. There are many interesting environments to play with. So at this point we look at Carracing. So the idea here is really simple. You are forcing the car to go over the whole track, okay, without going out of the boundaries. And you get the higher reward the faster you go over whole track. So it's kind of simple simulation. And then you can imagine that you have this car like a simple car and a track in real life, okay? So we are actually thinking already how to transfer these ideas to real life. Okay, and the general comment about current state of RL, there are many issues that needs to be addressed with new approaches, I think. The issues with RL algorithms, so there's lack of robustness. So you change a bit your initial position or parameters, and it breaks down, okay? It doesn't work anymore because there's no robustness. There's lack of repeatability. So someone wants to repeat my experiment and runs the code, and it doesn't work. That's really common in deep RL. There's lack of transferability. Even by transferability, I mean transfer to different tasks, okay? So for example, you have that car, and then you change that car to some car with 3 wheels instead of 4. And your approach doesn't work, okay? So that motivates me, okay, to search for new approaches and algorithms. So I didn't say that there's also a problem with sample efficiency. So you want to train as fast as possible your models, okay? So there's the approach which is really interesting is so-called model-based approach. So this is like an abstract slide. So in general, model-based approach. You have your environment. Environment, by the way, I showed you this simple car racing problem. Environment can be anything. It can be a computer game or whatever, some adversary, some policeman and thief game, whatever. So what's up with model-based RL? So there's like environment and controller which provides policy, okay, how to control your environment to achieve the highest reward. And there's like intermediate step, which is a world model, okay? Because maybe I want to construct a world model first, okay? Or I want to provide some insight into my model about my environment. Not to only derive policy by interacting with environment, because it's hard, and it's really not sample efficient at this point. So I want to put in something, a world model, okay, which will model behavior, and then by having that, I can extract a policy easier, okay, from that model. And as you see, it can be like an ensemble of different models. Why not? And there are some ideas what can be model. Simple, what people are using now is like recursive neural net, LSTM, transformer network, or really interesting another possibility. There's this paper about neural ordinary differential equations, which got the best paper award at NIPS conference in 2018. And this is interesting idea, which is generalization of recurrent neural networks that can be applied, I think, as a model. Okay, so people for Carracing, there already exists approach. This is really popular paper from NIPS conference also, and they construct exactly this with recurrent neural network. Okay, and one application they have is Carracing. And so let's see how it works. So we repeated the results, and that's how it works. So this is the train policy. The car tries to go over the track. It's really wobbly, unstable, and it gets up to this point. Okay, we're training this on our computer in the lab, and we got like 760 or something score. They report 900, okay? So it means they were able to do it faster. Maybe they got lucky, I don't know. But anyway, this is already good that we could run exactly the same pipeline that they did and get a reasonable score, okay, on that problem. So there are some issues. As you saw, this policy is really unstable in a sense. As you see, there's action. It's telling the car to change, the angle of the wheels really rapidly, and the car gets really wobbly, unstable. It's still poor sample efficiency for this simple problem. It took days to train this approach, and there's another issue is it's not clear what is the benefit of using the model, which is LSTM in that case. So, okay, so that's my favorite slide. So let's see. Idea is I want to do some human engineering and put some information into my reinforcement learning agent, okay? Which is, in that case, some rough physical intuition or rough physical model. And I'm putting that into my engine, and let's see. So this is just sneak preview, okay? This is sneak preview of our approach. This is just proof of concept. We use a lot of heuristics at this point, so it's not publishable. But the idea is that, so we want to use that bit of human engineering and to kind of prescribe the model how car works, okay? And then if car has a checkpoint, we know how to control it to find that checkpoint, okay? And of course, the model is like general, so there need to be some fitting of parameters in the model, etc. But in this approach, the agent, okay, is composed out of two modules, okay? There's one module which is generating checkpoints, kind of. So that module is supposed to figure out that if checkpoints are close to the middle of the road, you get the highest reward, okay? Because then the car gets the fastest. Or if there's a turn, you should go close to the left, to the closer side, right? And things like that. And at this point, we use heuristics for, okay, what you see here is this like recorded. We use heuristics for that, but we are implementing neural net, okay, now, which is gonna do that job, how to figure out the checkpoints. And as I said, once I know the checkpoints, I put in some model into my approach, and then the model will tell me how to, cross that checkpoint. And hopefully, I mean, that will be, okay, there are many opportunities. Okay, you can see actually, oh, this is the prediction. As I said, I put that model in, and so you can see the car can predict how it will go, okay, on the track. That's the second part. Sorry for the resolution, but that's the idea, okay? There's a checkpoint, and the car learns that it needs to drive straight here to cross that checkpoint, which is in the middle of the road. But then there's a turn, so it kind of predicts. It's correcting a bit still, but it's not perfect. But the idea is that, okay, you can see a turn. It kind of figures out that it needs to turn because it knows kind of future, okay? Because there's this modeling part that was human engineered. So, of course, there's a bit of supervision because I'm putting that model in. But there are many opportunities, which is, one of them is improved sample efficiency. Second thing is stability. You already see it here, that this car kind of, if the road is straight, it goes straight, okay, which is good, because it was not the case in the previous approach. And this disappeared. Yeah, and we hope for better robustness and transferability of that approach, and maybe do some few-shot learning for modified environments. Of course, this is not state-of-the-art problem. It's simple game, okay? So you can say it's silly to focus on that, but actually, yesterday or like 2 days ago, I got a gift from OpenAI. So they released another environment which is called Safety Gym, okay? So it's a gift for me because I can use my knowledge from the previous research with this safety verification, you know, hopefully. And the problem here is you need to steer the car such that it hits, buttons, and it avoids some areas. It cannot, there's like a hole, for example, okay? And if you drive there, it will drop and your reward will be negative, okay? So it's not only about hitting some simple task, but there's also area to avoid in that problem. And there's also one way of, they have 3 different objects. One of them is a car, so we can apply the experience that we will get from car racing to that environment, hopefully. So, any questions? Yeah, so that's the next goal. And the last part, let me mention, that's I got recently involved into research on performance factors in esports. So, the esport is becoming a big part in machine learning. The recent result with AlphaStar playing with on Grandmaster level in StarCraft 2. And this is like really big in science community at this point. So I think esport is really also good direction. So I started collaborating with that company called Esports Lab. And I have just 2 slides about that because I just started doing that. So there's like a lot of competition and prizes involved in esports nowadays, and no one knows how to train actually. So if you have like sport competition like running or basketball or soccer, whatever, people know how to train, okay? And there's methodology. And for esport, although it's projected to become as big as soccer in several years, and no one knows how to train. So we kind of are working on there's a lot of responsible for machine learning research, okay? I don't know much about other aspects, but there are many aspects involved, as you can see. There's cognitive aspect, there's psychologists working on that, there's physical and mental health, and etc. And I will be working on machine learning. Reinforcement learning should be a part of that too. And yeah, so that's the general idea, to kind of be able to provide some insights how to improve your skill in playing some computer game, basically. Yeah, so I guess thank you for your attention, and if you are interested in updates, you can follow me on Twitter. So thank you.